Hello, this is Mr. White, and this video is on using the FTC, or Fundamental Theorem of Calculus, to evaluate definite integrals. Here are the three exercises for this video. In our first example, this is a fairly small exponent up here, a 2. If that were bigger, if that were, say, a 12, we're going to be glad that we'll be learning something in the future called integration by substitution, or in this particular case, I would call it the unchain rule. And we're going to be glad that we learned that because we don't really want to have to distribute out that binomial 12 times. However, in your first experience with using the FTC, I would encourage you just to rewrite whatever expression, whatever integrand you're given, rewrite it in a way that you can just unpower rule it. So in this case, just FOIL that out. And again, we'll worry about more advanced techniques later. We FOIL that out and we get 9x squared plus 42x plus 49. I have not done any calculus yet, and that's why I still have the integral symbol and the dx at the end. And remember to think of those as sort of like an open and a closed parentheses. If you have one, you need the other when you're doing the FTC. All right, so at this point we'll do the calculus. At this point we'll antiderive, and that first term becomes x cubed, and that means that there's a 3 in front. I just pause and mentally derive that to make sure it brings me back to that 9x squared, and it does. Again, that's a habit you should be in by now. Second one, x squared, and therefore there must be a 21 in front. And finally, 49x. Now, I'm sure I've mentioned to you that you don't need the plus c at the end, but just for the sake of this example, just in case you didn't catch why we don't need the plus c, I'm going to put it in here for this first example. But again, I'm putting it in there simply to prove that you don't really need it when you're doing a definite integral with the FTC. All right, so I'll remind you that we then put, again, I like to put a bracket. Some books will just put a single vertical line at the end, but I like to put the brackets and then put the 1 and the 0, the limits of integration on the outside there. And that means that we'll plug in the 1 first and then the 0 second, and we'll subtract those two quantities. So if I plug in the 1, I get quantity 3 times 1 cubed, that's just 3, right? And just for emphasis, let me put the 1 cubed in here, just so you really see exactly what's going on. So I just plug in the 1 everywhere where I see an x, and make sure you do a closed parentheses or closed bracket. I don't really care whether you do a parentheses or bracket, but some sort of grouping symbol. And then minus, and now you plug in the 0. And again, I know you can do that quickly in your head, but just to really emphasize what exactly is going on, I'm going to plug it in here. Oh, you know what? And I made a big deal about that plus c, and then I forgot to do it, didn't I? Well, I'll squeeze it in there here at the end. All right, so what I should have done is, since I made a big deal about saying I was going to put a plus c in there, I should have had a plus c here and also a plus c here. And what that means is that in the end, when I just do this arithmetic, I've got 3 plus 21 plus 49. Don't forget to distribute that negative. Plus c, right? And when I distribute the negative, I get minus 0, 0, 0. But then that second plus c over here becomes a minus c. So that will always happen. The plus c in the first set of parentheses will always be have a minus c along with it. So that's why I said we don't really need the plus c. Anyway, 3 plus 21 plus 49, that's going to be 73. And that is our final answer. So unlike indefinite integrals where when you don't have the little numbers next to the integral symbol and you get an actual function plus c, in this case, with definite integrals, you get just a number. And I really want to emphasize and make sure you understand what that number means. Remember, that is calculating, well, what's often summarized as the area under a curve. So let's get the calculator up here, and this is something I'm going to want you to check regularly, get in the habit of checking. Let's put 3x plus 7. And I want to remind you, you're typing in the original the original integrand here, the 3x plus 7 squared. Often students get confused and type in the anti-derived, the 9x squared plus 42x plus 49. No, we're typing in the original there. And I'm just going to go to, I'm looking at my limits of integration being 0 and 1, and I'm going to go zoom number 4, zoom decimal. And I clearly see, this shouldn't surprise me given our pre-calculus skills. I see that this is a transform parabola, and I can tell that once I get to 0 and 1, I'm going to get some fairly high y values. Visually, you can just tell that. And so the way that I like to determine my window settings is I'll go to trace, and I'll go to 0, and even better, let's go to 1. And I see that my y value is 100. And so that means that my y max, if I want to see this, my y max needs to be at least 100. So let's go to window, and let's change the y max to, let's do 120. And hit graph. And then we can go to second calc. And again, this is a little bit deceptive on the calculator's part, just due to space constraints. That option number 7 looks like an indefinite integral because it doesn't have any numbers, any a and b, or 0 and 1 in this case, next to the integral symbol. But it really is a definite integral. That's all your calculator can do, at least TI-83, TI-84 model. So lower limit, I'll put 0, enter, 1 for the upper, and confirmed, the answer is 73. That's what we got. All right, so that's example number 1. Let's go to example number 2, or example B as I have it here. Once again, at this stage in your FTCing, you just need to rewrite such that you can anti-power rule this. So remember that with a fraction written this way, you can do u over square root of u plus 3 over square root of u. And that's exactly how we need to rewrite this thing. So let's say that's the integral from 4 to 9. Again, we're not doing any calculus yet, so I still do the integral symbol of u over, let me go ahead and write that as u to the 1/2. And just for emphasis, I'll put a u to the 1 up top, plus 3 over u to the 1/2 du. And that can be rewritten once again as integral from 4 to 9 of u to the 1/2. You better know your exponential rules well here. Plus 3u to the negative 1/2 du. And now I will unpower rule this thing. So that u to the 1/2 will become, now I'm doing the calculus, so I won't do the integral symbol anymore. That'll become a u to the 3/2, and that means that there must be a 2/3 in front. Just stop and I'll mentally check that in my head, and yes, it does give me this integrand term. And then the second one will be plus that u to the negative 1/2 will become a u to the positive 1/2. I've just added 1 to the exponent, and that means that there's really a 2 in front, but oh, what about that 3 over here? Okay, so instead of 2, we'll make this a 6. And again, if you don't clearly see that, just derive this in your head and verify that you do get this integrand term over here. All right, and all that is from 4 to 9. And I'll come back over to the left side of the screen, and when I plug in 9 there, we see, okay, I'm very glad that I have perfect squares here. That makes it nice and neat. Well, let me just do this. 2/3, 9 to the 3/2, and then I'll remind you of these exponential rules here. I'm going to do it a little bit differently than I did in the last example, and I'll invite you to decide how you choose to go about this. What I'm referring to is I'm going to plug in the bottom now, but instead of doing everything in terms of big parentheses, I'm just going to plug in the bottom, and by the bottom I mean this 4 here. 2/3 4 to the 3/2, and I'm going to distribute that negative sign. I'm going to distribute this negative sign right here, and therefore make this a -2. If you're not comfortable doing that, do the big parentheses, 4 to the 1/2. Okay, let me scroll down a little bit here. Okay, so 9 to the 3/2. The way I like to think of that is 9 to the 1/2 power. That would be 3. and then raised to the third power, so that's 27. So 2 times 27 over 3 would give me 54 over 3, and that would give me just 18, right? Okay, so bottom line is you see how good it is to have the mental math down, but do what you need to do to get that correct. Likewise, 9 to the 1/2 power is just 3, and then times 6 is 18 again, coincidentally. Minus 4 to the 1/2 power is 2, but raised to the third power is 8. 8 times 2 is 16, and that is over 3. And then 4 to the 1/2 is 2, times 6 is 12. So I get a bunch of terms there. Only one of them is fraction. Let's combine those first. 18 plus 18 is 36, minus 12 is 24, so I'll put 24 minus 16/3. We can combine in whatever order we want. And then that is the same as 72 over 3 minus 16 over 3. And that gives us, let's see, that's going to give us 56 over 3. And that is our final answer. And just to make sure I haven't made any mistakes, I'll show you that the same deal. This time I'll just bring the results up here. This is the calculator's version of the definite integral. And 18.666666 repeating, that is the same as 56 over 3, so I know I've done this correctly. All right, one more example. This one. This one it could really trip you up if you're not careful. At first glance, I don't know, maybe to a student, maybe it doesn't look too bad, but let's carefully go through this one where we have the cube root of quantity 5 over t minus 4 being integrated from 1 to 8. All right, first thing I want to do is rewrite this integrand. So I'll still be integrating from 1 to 8. But I'm going to rewrite it this way, and pause the video if you need to. Make sure you understand why I'm doing this. I'm going to write this as 5 to the 1/3, because that 5 up there in the numerator is being affected by that cube root, right? So that's 5 to the 1/3 t to the negative 1/3. Notice how the t is affected by being in the denominator over here. That's like an exponent of negative 1. And then there's that 1/3, that cube root, so negative 1/3. Not really anything I'm going to do that for, so I'll just do minus 4 dt. Okay, and now I'll antiderive. The main thing that I see students messing up is, for whatever reason, students tend to mess up that 1/3, that 5 to the 1/3. Remember, this whole thing, that whole 5 to the 1/3, is to be treated as a constant because, well, it is a constant. All right, so this t to the negative 1/3, when I antiderive that, that'll give me t to the positive 2/3. And I'm going to take it just a step at a time here. I'm going to put the 3/2 in front. And then I'll just write this 5 to the 1/3 out in front. Not really any way I could combine that 5 to the 1/3 and this 3/2. Just for emphasis, I'll put that in parentheses. Minus 4t. And then, again, I like to put the whole brackets around there from 1 to 8. All right, let's plug in the 8. And again, that 5 to the 1/3, it seems to make students uncomfortable that we can't simplify that or it doesn't go away, but we just have to deal with it. 3/2, 8 to the 2/3. Let's see, I need another closed parentheses, don't I? Minus 4 times 8. And again, I'm just going to do my preference of distributing this minus sign. So minus 5 to the 1/3, and then 3/2, 1 to the 2/3, and then minus 4 times 1. Okay. Oh, I made a mistake, didn't I? I hope you caught that. I find I sometimes cannot do math and talk at the same time. What a curse. Anyway, that's supposed to be a plus there. I hope you saw that right there. I made a big deal about talking about the minus sign, and then or distributing the minus, and then I went ahead and didn't do it. Brilliant. All right, I think that's all correct, though. That's why we check on calculator, right? So this is 5 to the 1/3, and again, 8 to the 1/3 would be 2, and then squared would be 4. 4 times 3 is 12, divided by 2 is 6. Minus 4 times 8, which is 32, minus 5 to the 1/3, and then times 3/2, plus 4. Okay, don't have a lot of choice. This 5 to the 1/3 occurs in two places, and I've got a 6 minus a 3/2, so that's like a 12/2 minus a 3/2, so that's 9/2. And again, I'm just doing the mental math here. You do whatever you need to make sure you get a right answer. Minus 32 plus 4 is going to be minus 28. And again, it may bother the student, but you really can't do anything more than that. That is our final answer. If I were to check that via calculator, I would get this. And I will go ahead and confess, there is a way to do definite integrals on the calculator just directly rather than the graphing method, but I'm showing you the graphing method because I strongly prefer that you do it that way. I want you to visually see what we are computing here, that we're calculating the area between a curve and the x-axis. I want you to see that. And then as we get more comfortable with it, I'll go ahead and admit that I'll often use the more direct way of doing a definite integral on the calculator. But I wanted to acknowledge it. If you have a student, a peer of yours, say, hey, why don't you just do it this way? This is kind of like the birds and the bees talk. I'd rather at least acknowledge it to you and tell you my cautions and my advice that you just do it the way that I've been showing here, graphing the original integrand and going to calc number 7. Please do it that way for at least your first few assignments. If I wanted to confirm that that was my correct answer, I could also go up here and verify that that ugly expression typed in the calculator does give me the same result that we get when we go to calc number 7. All right, hope that was helpful. If you still have questions, come on by to office hours.